next we'll move on to question 2, which is also a relatively interesting question. Okay, so for question 2, you are asked to account for the observation that the slow rate of hydrolysis of a primary chloroalkane can be markedly increased by adding a small amount of Ki. So obviously this particular reaction takes place in an aqueous medium. Yep, and take note that it's very, very slow if you simply just involved chloropropane and water, but the reaction rate will accelerate if you increase, or rather if you add potassium iodide into the solution. Yeah, so the first thing I think we need to come to terms with is that H2O is the nucleophile. Okay, so it's the key nucleophile we have in this particular system. Yeah. So in some of the scripts, or in quite a number of scripts which we have marked, we notice that students use hydroxide as the nucleophile. Yeah, take note that this is incorrect, because how can I generate hydroxide between H2O and say Ki? Remember that Ki, right, is an ionic compound. It's an ionic compound. Yeah, so in aqueous medium, what you're going to have here is simply K plus aqueous and I minus aqueous, which is iodide aqueous. Yeah, so iodide being the conjugate base of a very strong acid, which is Hi, will never be able to generate OH minus when it reacts with water. In fact, I minus will simply be solvated by water, but it will not undergo hydrolysis with water. Yeah, so remember some of the things you have learned from acid-base equilibrium is very, very important. Okay, so this being a conjugate base of a very strong acid, okay, so it will not be hydrolyzed. Remember this. Okay. Yeah. So in this case, how can we make sense of the reaction? Yeah, I think we can make sense of why is it slow. Okay, so it is slow because number one, we have a very poor nucleophile. So water in this case is a poor nucleophile. Yeah, so you have to emphasize that water is a poor nucleophile. That explains why the first reaction is very slow. Yeah, and the reason why the second reaction becomes fast is because I expect iodide, right, to be a stronger nucleophile than water. Okay, so again, iodide is a stronger nucleophile than water. So when I add in iodide, what is going to happen is that the iodide will undergo or will perform a nucleophilic attack on the chloride. So in this case, it will attack from the rear, okay, and then the C cell bond will break. And in the process, I'm producing the iodopropane, of course, plus Cl minus. Yeah, and iodopropane, right, as all of you know, because iodine is a good living group. Yeah, so because iodine is a good living group, a poor nucleophile, such as water, right, will be able to attack it from the rear again and then cause iodide to leave. Yeah, so I think after a while, you should be able to get the correct thinking of mechanism in the right place. So for example, if I have a poor living group and then I have a weak nucleophile, then obviously the reaction will take a long time. Then how can I accelerate the reaction? Okay, I can accelerate the reaction by doing two things. First, I can make the nucleophile a stronger nucleophile. So instead of water, I can use OH minus. Yeah, but in this case, I do not have OH minus. Yeah, so if I do not have OH minus, what do? Then I'll make chloride a better living group. How can I make chloride a better living group? By replacing it with the better living group in this case. But the better living group also tends to be a poor nucleophile. So in this case, we have the best of both worlds, because iodide is itself being highly polarizable, right, is a better nucleophile than water. So in this case, iodide can replace Cl, but because the Ci bond is weaker than the CCl bond, so that makes the bond being more easily broken, and iodide is a good living group as well. So this particular reaction will take place when water will displace iodide. Okay, so in the process, I'm going to generate the conjugate acid of the required alcohol. And of course, the next step is obvious, because the OH bond will simply be broken, will probably be grabbed by a water molecule, and then in the process, I'm going to produce propane 1-ol. Okay, so if you look at if I attempt to draw the energy profile diagram, I think it will be much clearer to you. So in the energy profile diagram, right, we have energy here, okay, and then we have reaction coordinates. Yeah, so let's say we have let's say in our case here, right, we have a good living group. So we have a living group here. I just put LG as a living group. Okay, yeah. Then if I'm going to allow nucleophilic substitution to take place with, let's say, the iodo, yeah, then it will probably look something like this lah. So the profile diagram will go up, and then it will come down like this. Okay, so this is the one where I'm going to get iodo here, and then plus the living group. Okay, then we can look at another pathway where I'm going to use chloride as the nucleophile. Okay, but obviously the activation barrier will be higher. Okay, and then but CCl bond is stronger. So in this case, I'm going to get Cl here and the living group here. Okay, so you'll notice that iodides being a better nucleophile, yeah, will have a lower activation barrier leading to the products. So this is the EA. Okay, but of course the Ci bond is weaker lah. So if you consider the reverse reaction, obviously it will have a lower activation barrier as compared to that between the chloroalkane and the living group. Yeah. Okay, so with that, we have come to the end of the debrief to question 2.